gauge theory and relate to the strong coordinate system?
Oh, yes.
Because I remember that you have talked a little bit about the relation about strong coordinate system.
Yes.
Thank you.
Okay, so there are many things I can say, but so I can say one thing I try to mention is anomaly is related to gauge anomaly is related to symmetry property topological order. So that's the first thing I can mention. But that thing means that if I have some states, what you study like a topological insulator in the bulk, then it just means there is some kind of anomalous current flowing on the boundary. If you try to understand the symmetry of this edge states and then try to gauge the theory, what does that mean to gauge the theory? It means that making this symmetry variable depends on the site. Then you make the theory from global symmetry to gauge symmetry. The gauge symmetry will relate to SPD states. So that's related to what I say about the talk. But there's also many things I can say about the relation between gauge theory and the topological insulator or topological order. For example, people know Kitev studied those, he won this fundamental physics prize, the 3 million prize. The reason he proposed this topological quantum computation, the model he has is so-called this Z2 torical. The Z2 torical turned out to be a theory that one can study by using Chen-Simon theory, break down the Chen-Simon theory U1 symmetry to Z2 symmetry, and that theory we'll call Z2 gauge theory. So the relation between what you study about on the lattice, like Z2 torical, I don't know, maybe some of you might study that. So Z2 torical, the thing that you put on the spin on the side with some coupling about sigma x on the vertex, and then some sigma z on the links, and then with this one is like sigma x and this one sigma z. Those theory can induce emergent gauge theory correspond exactly in low energy as a Z2 torical, Z2 gauge theory. And the Z2 gauge theory can be constructed by breaking down the U1 by some Higgs term, for example, U1 break down the term. And this Z2 gauge theory just nothing very similar to what you study about superconductor, because superconductor exactly aiding the term to make the U1 symmetry break down to Z2. If you remember, the superconductor has this kind of term, and with some Hamiltonian or coupling, right? In the early morning, we learned this, we heard this from Professor Ye. But the coupling exactly aided the term is in superconductor, BCS type superconductor is this. The symmetry transformation for the free part is a rotation about arbitrary EI theta, right? Because these two will cancel, conjugate E minus I theta and EI theta will cancel. But this term is exactly the term make theta equal to pi. So in a sense, what you have about Z2 gauge theory is almost like a superconductor. But the difference is superconductor, the gauge field is not dynamic. So it's different from what we study about torical from the Kitev side. But there is some relation about the thing you know about BCS superconductor if you make the gauge field dynamical. So yeah, so there is some relation about people studying quantum information about torical actually is related to high energy physicists study this discrete gauge theory. And is there something else? This is probably two comments I can give. So there's an emergent gauge theory from the lattice. You can do this, and it's well known. You can even have emergent anions from this spin, and basically there's some way to draw this string of this on the lattice with some excitation, and those string excitation will correspond to the anions, and the braiding about this anions exactly give the AB phase and calculate from the Z2 gauge theory, from Chen-Simon theory approach. And theoretically, this understanding is quite well known, and I think experimentalists are driving also in this direction. Thank you. That's some other question?
Okay, let's thank our speaker again. So each kind of 15 minutes break.